Today I'll explain the electronic configuration of chromium and copper using a question. The question states, chromium atomic number 24 and copper atomic number 29 are well-known exceptions to the Aufbau principle. A says, write the expected and actual ground state electronic configuration of both elements, and B, using the concept of exchange energy and orbital stability, explain why half-filled and fully filled d subshells are energetically favorable. First, let's write out the electronic configuration of chromium. That's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5, which can condense to Ar, which is argon, 4s2, 3d4. Now, the total number of electrons here is 24. According to normal electronic configuration, this is the expected electronic configuration as stated by question A. Is what we expect, but there is something we call the half-filled and fully filled stability of d orbitals. What do I mean? Now, when a d orbital is half-filled, meaning that each electron are unpaired, all 5 electrons in the d orbital are unpaired, and therefore they can exchange orbitals. So we can have electron maybe in the first orbital moving to the second or the third. This exchange in orbitals releases a very small amount of energy. So the exchange you undergo releases a small amount of energy as compared to when an electron that is paired is to exchange or to move to an orbital that is unpaired. That requires a greater amount of energy. So if those small amounts of energy which unpaired electrons release when they exchange, if you add them up, it requires less energy for that atom to be stable. So meaning that the best stable electronic configuration for chromium is actually when 3d4 is half filled. Now, it requires one electron for 3d4 to be half filled, and that one electron is gotten from the 4s2 orbital. So one electron transcends, or rather it descends since it's at a higher shell, to the 3d4 orbital and then occupies the last orbital. So all electrons are unpaired and the exchange energy between them is low. So if the exchange energy is low, the sum of the energy becomes low, and therefore the atoms become stable. As for copper, the same thing applies, but in the case of copper, instead of the half-filled stability, we have the fully filled stability. Let us write the condensed electronic configuration for copper. We have Ar, 4, which is argon, 4s2, 3d9. So we have 9 electrons, a total of 9 electrons in the 3d subshell. Now that 3d subshell now, or 3d orbital, can contain a total of 10 electrons. That's when it's fully filled. But if one electron comes down from the end shell, that is the shell that is just above it, if it comes down to it and occupies the last orbital, we're going to have that it becomes 3d10. So 3d10 is fully filled and 4s1 remains, so because that's when the electron came from. So we are going to have Ar, 4s1, 3d10, which is the stable electronic configuration of copper, more stable than what is expected, and this is due to the same concept, which is what? The exchange energy concept. Now this exchange energy is what brings about stability in the orbitals. The exchange energy is less when they are between unpaired electrons or paired electrons, so it takes less amount of energy for them to exchange between each other, and this results in a total sum of the energy. The total sum of the energy becomes less than the expected value. So what we expected, the total energy is greater, but the actual value, the total energy is less. And remember that stability is the goal of every element, and therefore the atom is more stable as compared to the expected configuration. For B, D of question 1, it says, using the concept of exchange energy and orbital stability, explain why half-filled and fully filled d subshells are energetically favorable. The same concept applies as I already explained exchange energy in question 1a, but let's talk about it in details. Now, when half-filled or fully filled, a subshell, like the d subshell in particular, it's stable due to orbital symmetry. Now, what is orbital symmetry? Electrons are negatively charged, and according to electrostatic interactions, like charges repel and unlike charges attract. Therefore, if electrons are negative and possess the same charge, they should repel, and this electron-electron repulsion creates a sort of pressure in that subshell. Pressure, it is unbalanced if and can also be unbalanced. It's unbalanced if it's equal in all sides, not equal in all sides, but it's balanced if the pressure is even all round. So let's take the case of a half-filled d orbital. It's even and it's balanced due to the fact that in the d orbital, the electrons which have the same repulsion to each other. So this creates a symmetrical orbital, which effect of the electron repulsion all around is the same. Think about it like a five-seater table where you have about 5 people, like in case of the half-filled d orbital, sitting in a chair. Now, if all 5 are occupied, it's going to seem psychologically right that this is a perfect setting. But say if one person leaves, as much as creates more space for other people to come or for other to shift, it creates sort of like an unbalanced, it's psychological effect. It makes it unbalanced. Why? Because its number, it's not odd. Yes, the five-seater table, one having 4 people, but if another person leaves, the effect comes back. We now have 3 people, equal spaces between them. So a very similar thing occurs with electron repulsion. Half-filled orbitals have the same repulsion, same effect on each other. So this creates a stable orbital, and of course it's known as orbital stability. So the same thing, or rather similar thing, occurs in fully filled d subshells. Alright, let's go to question 2. State electronic configuration for the following species and identify which ones are isoelectronic. We have iron 2 plus, iron 3 plus, manganese 2 plus, cobalt 3 plus, and zinc 2 plus. Now, first off, we must understand what ground state and isoelectronic means. Ground state implies the most stable configuration of an element, or in this case, ions. So, which one is stable? Which one actually requires less energy to reach? And then they said identify which ones are isoelectronic. When 2 ions, I repeat, 2 ions are isoelectronic, they have the same number of electrons but different number of neutrons. Elements cannot be isoelectronic because in that case electron number would equal proton number, which of course no 2 elements can have same proton number excepting their isotopes, and isotopes are elements which have same atomic number but different mass number. That is caused by a difference in number of neutrons. But let's focus on isoelectrons, which are elements which have different proton number but the same number of neutrons. Now, iron 2 plus, the electronic configuration will be in the condensed format. So we have argon, which is the closest noble gas to iron, 3d6, 4s2. This is the ground state for iron. The ground state for iron contains 2 electrons in the 4s orbital and 6 electrons in 3d orbital. Now, when iron loses 2 ions, it loses from the outermost shell because those are the valent electrons and they have the least amount of energy. the one that takes less energy to remove. So when it loses 2 ions, it loses from the 4s orbital rather than 3d. So we're going to have AR 3d6. That's the electronic configuration for ion 2 ion. For ion 3 ion, it becomes AR. We already established that ion 2 ion has no electron in shell with n is equals to 4. If it's to lose one more, it loses from the shell below the n shell, which now becomes the m shell. That initially has 6 electrons, right? So if it loses one, it becomes 5. So we have 4 AR, 4s power 0, 3d5. The correct equation for ion 3 ion. For manganese 2 ion, it becomes AR 4s2 3d5. That's as the ground state. But when it loses 2 electrons, it loses from the outermost shell, not the one represented at the end of this configuration. That's 3d5. No, it loses from the 4th shell first. So it becomes AR 4s0, which can take as 1, 3d5. So that's the correct electronic configuration. Cobalt 3 ion becomes AR 4s2 3d7. As usual, that's the ground state. When it loses 3 ions, it loses 3 electrons rather. It loses 2 from the 4s shell, the 4th shell, and 1 from the 3rd shell. So that becomes 4s0 3d6. For zinc 2 ion, zinc 2 ion becomes AR 4s2 3d10. Now if it loses 2 electrons, it loses from the 4th shell as usual. Now that becomes 4s0 3d10. Now I would like to point out something. There is a common misconception that since zinc is in the D block, it should have characteristics of a transition metal. But the fact is that zinc has 2 possible oxidation states, which are +1 and +2. So when it is +1, it is 4s1 3d10. When it is +2, which is maximum oxidation state, it becomes 4s0 3d10. So since none of its oxidation states involves the 3d orbital being partially filled, that's a very important criteria for transition metals. The 3 orbital must be partially filled, and none of its oxidation states involve that. It does not have any characteristics of transition metals except it can behave as a catalyst. That's by the way. So the elements, or rather the ions which were identified as isoelectronic, becomes manganese 2 ion and ion 3 ion and ion 2 ion and cobalt 3 ion.